Hello, my name is Ernesto Chavez, and this is my optimization project of a weight optimization of a finite wing. I completed my project using CATIA V5 tools to generate my optimization project using design, analysis, and optimization tools in CATIA to minimize the weight of a wing. My background, the CATIA was mostly used as seen from an optimization standpoint. It's more of a geometrical and structural background kind of system and software. However, you can actually link it with C++ and OptiStruct. Several projects that you can see as C-hook, car tires, you can use with CATIA varying the geometry and structural integrities. And in common search techniques that are used to simulated annealing algorithm and grading algorithm. For this project, we did a simulated annealing algorithm to find a global minimum. The wing geometric bounds for the project, as you can see on the screen, is the wingspan, chord, and percent thickness. The critical thing here is a symmetric airfoil equation that had to be put into CATIA in order for all the parameters to be tied parametrically in order for the optimization workbench to work efficiently and give us our minimum weight. From a structural analysis perspective, we used a linear tetrahedron mesh to generate our analysis software, and we also applied a lift force and a fixed constraint to the wing to simulate the flight conditions. This generated the objective constraints of the von Mises stresses, deflection, and aspect ratios to the values you see on the screen. From a program optimization problem standpoint, we used the CATIA optimization workbench. This allowed us to use the minimization type to minimize our weight of the wing. Our bounds, we did a continuous search space using the chord, wingspan, and percent thickness with the values we identified earlier. In our algorithm, we use a stochastic algorithm as a simulated annealing algorithm to generate an approximate global minimum which is desired for this project. Identifying the constraints we put in the constraint window, and that will be the aspect ratio, stress, as well as the displacement. From a summary on the problem statements, you can see on the screen, this is a summary of what our project is entailed. And our search technique is the simulated annealing, which would be a stochastic search technique. Our flight envelopes will be three cases you can see on the screen. These will be the three variables that we applied to the wing and to generate our optimization problem to generate the best result. From the best way, you can see that actually the best from different cases. You can see the weight increase per each case, and this is not abnormal. This is what is expected. From a chord, you can see that actually ended up having the chord be more closer to the minimum values. It started out varying for all three cases, varying the chord greatly from all those ranges, but ended up going more towards a minimum value. From a thickness, the thickness actually was the most critical feature. From all three cases, the thickness actually varied through the entire search space to either to maximize the weight and also to meet all the structural requirements. The wingspan actually was a little interesting because it actually maintained the wingspan at a minimum level to generate the best result. And also it played with the aspect ratio and the chord to still maintain our aspect ratio, but ultimately ended up having to be the wingspan at its minimum. So aspect ratio actually played an important key. As we increase the aspect ratio, we can then potentially see a higher weight impact, even though we're actually increasing the efficiency of the wing. In conclusion, from our table of results, we can see that the best case, we can say is case 2. It generated a good weight compared to the performance of the wing, and it still maintained our aspect ratio and all our structural requirements. As you can see, the wingspan was contained close to its minimum, as well as chord, and thickness was the key player in order to minimize the weight and the structural integrity. Supplementary, we also did some further optimization to kind of understand more of the aspect ratio effects on the project. You can see the aspect ratio can vary from 2.3 to 4.7. This actually is interesting to know that as you actually lower the wingspan, just looking from an aspect ratio standpoint, we actually increase the weight. So you can see how the thickness and the chord play a much more critical role in the structural integrity of the part. Future work was add additional features to the part and run the optimization again to get a much more detail of the actual weight once we get more into the detail phase of the project. These are my references. Thank you.